Right, this talk is on Laplace transforms. Laplace transforms is a technique, mathematical technique for solving differential equations to obtain solutions in the time domain. And this technique involves converting the original differential equations, transforming them into some Laplace equations, solving them in the Laplace domain, and then taking the inverse Laplace transform to get back to our original time domain solution. So thinking is problem in the time domain, convert it to the Laplace domain, obtain the solution in the S domain, the Laplace S domain, take the inverse Laplace, and we get our time domain solution. So if we do have linear differential equations, we could go straight to the time domain if we were very clever, but we're not that clever, so we need to do Laplace transform, do some algebra, get the Laplace solution, and go back to the time domain. There's another technique for going from here to here called simulation, which uses numerical integration to do it, and that has been embodied into a package called Simulink, and we will be looking at an alternative way to get around this way, an alternative way using Simulink. And probably because a computer's been popular today, the Simulink domain technique is now surpassing the Laplace technique. But it's a very useful one to know, the Laplace. And this is the Laplace's equation. On face value, it looks quite a complicated expression, and one might think that carrying out this type of analysis is quite tricky. But fortunately, in practice, it turns out to be a lot easier. And one of the main things that we need to know is, as well as Laplace transforms for the system itself, which we now know is in the form of transfer functions, we'll also need to have a Laplace transform for the type of response we want from the system. Now, there are a number of responses we can have: impulse responses, step responses, ramp responses, exponential responses, or sine wave responses. So an impulse response goes up and then comes rapidly down, so just as an impulse of 1 unit. Step starts at one value, steps up to another. A ramp continuously increases. An exponential function increases exponentially, a bit like COVID-19. And a sine wave keeps on going up and down like this. So if it's COVID-19, it would come back as a second wave here. And the functions here are: impulse is s, is 1, step is 1 over s, ramp is 1 over s squared, exponential 1 over s minus a, and sinusoid 1 over omega squared plus s squared, where omega is the frequency. And we have to remember these when we're doing our Laplace analysis. So here are some of those. Step, Laplace transform of a step. There's 6 of these that we need to know to do the analysis. Step response is 1 over s. A ramp is 1 over s squared. This is a time domain. This is Laplace transform. Next one is an exponential, and e to the minus at is 1 over s plus a. And a t e to the minus at is with time in it as well, is given by 1 over s plus a squared. E to the minus at cos bt, this could give you a oscillatory type response, is given by s plus a over s plus a squared plus b squared. This process down here is called completing the square. So we have to have this as s plus something squared and a separate number in there. And you see the same term here in here to represent this particular term. So this one's more complicated, but we will use it later on. Sinusoidal term of the similar type doesn't have the s plus a here, it just has the b. So it's b over s plus a squared plus b squared. So we'll have to remember those 6 terms. So, and then we have inverse Laplace transforms, which is just basically the inverse of what we just seen. So inverse Laplace of 1 over s is 1. Inverse Laplace Laplace of 1 over s plus a is e to the minus at. Inverse Laplace of b over s plus a squared plus b squared is e to the at sine bt. And inverse Laplace of s plus a over s plus a squared plus b squared is e to the at cos bt. So these are the four main useful inverse Laplace transforms that we have to remember to do the analysis. And so this is how we could do it. First of all, we choose the type of response we want. So it could be, say, 1 over s. We get our transfer function gs, and then we multiply this by this to get an overall function. Then we take that overall function and we split it into partial fractions, and then we take the inverse time domain solutions, inverse Laplace transforms, and we'll get the time domain solution. So in principle, it's a little bit long-winded, but it does work nicely. Just to remind ourselves about transfer functions, so if we got a function like this, we could replace d2 by dt squared by s squared, d by dt is s, and we could go from this to a transfer function. So, and then just remember our types of input as well. So we've got the impulse, step, ramp, exponential, sine. The one tends to be used most of the time is the step, which is 1 over s. This is used 90% of the time, the step response. So let's take a simple example. Here we have 2 over s plus 4 as our transfer function. The type of step response we want is a step. So because it's a step, this is going to be 1 over s. So we then multiply this by this to get this term here. And then split it into partial fractions. I'll do some partial fractions for you, just remind you how to do them in the tutorial. And then having got from here to partial fractions, we then use the inverse Laplace transforms of each of these to get the time domain. So the 0.5 gives us the 0.5. 1 over s is just 1. So that gives us 0.5. 0.5 gives us the 0.5. And 1 over s plus 4 is e to the minus 4t. So this gives an expression now for the step response of this system as 0.5 minus 0.5 e to the minus 4t. What we've done is taken the original transfer function, multiplied it by the type of response you want, which is the step, to get this, split into partial fractions, then taken the inverse Laplace transforms to get the time domain. And this is essentially how you can go from a differential equation plus a type of response to a time domain solution using Laplace transforms. Here's another example. This time we've got 2 over s plus 2, s plus 4. Again, step response, so we multiply this by this to give us the overall function here. Then we take this function, split it into partial fractions, gives us 3 terms this time. The 0.25 is a 0.25, the 1 over s is a step, so that's 1, minus 0.25, minus 0.5, sorry. Then 1 over s plus 2 is e to the minus 2t, 0.25, 0.25, 1 over s plus 4, e to the minus 4t. So then we have an expression then for the step response to the system, and we could put different values of t in there, where t would be time, plot the graph out, and we would get the step response. In the case of a second order system where it can't be factorized, it can get a little bit more complicated. So let's have a look at that one next. So let's say we got s plus 1 over s squared plus 4s plus 5. We're looking at the step response, so it's going to be 1 over s. So we could take this function out, split it into partial fractions. We could use like different techniques for getting the coefficients. One is to compare coefficients of different orders, like coefficients of s squared, coefficients of s to the 0, and then compare both sides. We'll look at those techniques in detail in my little revision lecture. But let's assume we've gone from here now. Here's our partial fractions down here. Now, because it's a second order system, this one now has to have these type of responses in, which means we have to take this function here and split it into 2 parts. So this function has to be split into 2 parts, one to represent the sine, one to represent the cos. So we complete the square, so it's s plus 2 squared plus 1 on the bottom of each. That's converting this into this. But now we need an s, because we've got an s plus 2 here, we need an s plus 2 there as well, and a number in there. So we have to find that number and that number then by solving this equation. So again, I'll show you to do that. But in this particular case, it comes out as 0.2 and 0.6. And then when we take the inverse Laplace transforms, we've got the a alpha, which is this part here now, so it's going to be 0.2 over s, that's going to be 0.2. And this part here minus 0.2, and this is e to the minus 2t cos t. So it's that number there goes in there, and that number there goes in there. And this is a sine term, so it's 0.6 e to the minus 2t sine t. So this is a slightly more complicated expression now, because for a second order system, we get a sort of a response oscillates, and in oscillating, it has to be represented by a cos term and a sine term. Here's just a little bit more detail on that last bit of analysis, but we'll go over this in the tutorial which follows immediately after this.
Right, this little talk is on recap of Laplace transforms, and there's a number of things we need to know when we're doing Laplace transforms, but overall it's quite a complicated analysis, but it's actually quite simple to do. And the idea is we've got some linear differential equations which we want to have a look at the time domain solution for. So time domain is usually a graph of output against time, and we call this the transient response. So we might be interested in having some certain type of input going into our system and knowing what the output looks like. And in Laplace transforms, the main three inputs that we can apply are an impulse, and the Laplace transform that is 1, a step, which is 1 over s, and this is the one we use 95% of the time, and a ramp, 1 over s squared. So we have different types of input, and we can then obtain for different types of input transient responses. Bit of a spider there. Now, the other thing we'll need to know is, when we've done our analysis, we'll need to know a little handful of inverse Laplace transforms. And the inverse Laplace transform of 1 over s is 1. The inverse Laplace transform of 1 over s plus a is e to the minus at. And then we have a couple of second order terms here, which have got sines and coses as well. So this is b over s plus a squared plus b squared, which is e to the at sine bt. And s plus a over s plus a squared plus b squared is e to the minus at cos bt. So these are 4 things, inverse Laplace transforms, we need to use. And these are the 3 main inputs. And then we can, with that bit of background, we can do some problems. So say we've got a differential equation, which is, let's say, dy by dt is minus 4y plus 2u. And what we wanted to do now was to obtain the step response for this differential equation. So at face value, this looks quite hard. But if we deploy now our Laplace transform technique, it becomes quite easy. So the first main trick with Laplace transforms is to recognise that d by dt is represented by the Laplace variable s. So we can replace dy by dt by sy equals minus 4y plus 2u. And then we can collect up the y terms. So you get s plus 4 times y equals 2u, or that y is 2 over s plus 4 times u. So what we've essentially done now is we've got ourselves a little transfer function here. Now we've got the transfer function, we can then decide on what type of input we want to get the different types of response, and we're going to go for the step response. So we now multiply this step response by the transfer function, split it into partial fractions, and then take the inverse Laplace transform, and we'll get our time domain solution. So let's have a go at that. I just need a bit of space now to do this in. So we've gone from our linear differential equation to a transfer function, which is 2 over s plus 4. So let's just rub this out. It's not rubbing out so well, this. This is a bit of a problem. Got a new pen and it's a bit more nasty to rub out. Anyway, here we go. So we've got 2 over s plus 4 is our transfer function. And we've got a step, which is 1 over s. So we'll multiply that by s, it's going to be s like that. So next stage now is to split this off now into partial fractions. We can write this as a over s plus b over s plus 4. And now the only tricky part now is working out a and b. So to get a, we can use the cover-up rule to do this. So to apply the cover-up rule, we cover up, say we're working out the a, so we cover up the s here, and if we solved the equation s equals 0, we get the solution s is 0. So if I cover this up and put s as 0 in here, I'll get 2 over 4 plus a 0, so that gives me a half. So a is 0.5. To get b, b is associated with s plus 4. If I solve this, s plus 4 equals 0, I get s is minus 4. So what I do now is I cover up the s plus 4 here and put s as minus 4 in there, so it's 2 over minus 4. So b is minus 0.5, 2 over 4 with a minus in is minus 0.5. So I've now got my solution to my things. It's going to be 0.5 over s minus 0.5 over s plus 4. Then, having got to this stage, I now look for my inverse Laplace transforms. So I've got a 1 over s term is 1, so that's a 1 over s term there, but it's multiplied by 0.5. So I get y of t now, the time domain response. This equation now is this output graph here, y of t against time, and it's given by 1 over s is just 1, and 0.5 times 1 is 0.5. It's going to be 0.5 minus, and I've got a 0.5 here, and a 1 over s plus 4 is e to the minus 4t. And this now is the equation that describes the time domain behaviour of the system for different values of t. So we can now put different values of t in there, plot the graph, and we get a time domain solution. And in this particular case, it would probably look something like this. Like that. And if we make t very large here, e to the minus 4t would disappear, so it's going to go to 0.5. So that value there will be 0.5. So this is y of t against t, and it will come up to about a half. Well, come up to exactly a half. So this is an example now of where we could have gone from a differential equation to a time domain response using Laplace transforms. Right, so just going to look at another example now of going from a differential equation to a time domain solution using Laplace transforms. So we've got a differential equation, let's say d2y by dt squared plus 3 dy by dt plus 2y equals, let's say, 4u. So these are what looks like a second order differential equation now, and we're going to try and get the time domain solution to this. So the first thing we need to do is write another term here, is to convert this now into a transfer function, then choose the type of input, multiply the input by the transfer function, say the inverse Laplace transforms, and get our time domain solution. So let's have a look at doing this. So d2y by dt squared will be replaced by s squared, so get s squared y plus 3sy plus 2y equals 4u. So we convert our differential equation into a polynomial. We can then take the y out as a common factor. So it's s squared plus 3s plus 2 times y equals 4u. Unfortunately now, this one factorises into s plus 1, s plus 2. So we can now finally get our transfer function, which is that y equals 4u over s plus 1, s plus 2. Having got to our transfer function now, we can choose the type of response we want here. So we're going to go for a step response again. And we're going to multiply the step response by the Laplace transform, split into partial fractions, take the inverse of Laplace transforms, and get the time domain solution. So again, I'll have a bit of space here, using a slightly different pen this time, so it's easier to rub out. So we've got 4 over s plus 1, s plus 2, that's our transfer function. And we're multiplying it now by a step response, which is 1 over s. So we get a little s in there. And this now we can represent as a over s plus b over s plus 1 plus c over s plus 2. And our trick now is to work out ABC using partial fractions. So, first one is s is 0, s is minus 1, s is minus 2 if you solve those equations. So to get the a, we cover up this one and we put s as 0. So 4 over 2 is 2. So a comes out as 2. That's handy. Next one is this one. So this is equivalent to putting s equals 0. This is s is minus 1. This is s is minus 2. Into this function, covering up the appropriate one. We're using this cover up rule. To get the b, we cover up the s plus 1, so cover that one up, and now put s as minus 1 in here. So I get 4 over minus 1, then minus 1 and 2 is 1, so that comes out as minus 4. So that's quite nice. It's going to be minus 4. Then, to get the c, we do the same thing. We need this term here, this one, so c is the plus 2, so we cover this one up, and now put s as minus 2. So get 4 minus 2, minus 2 and 1 is minus 1. So minus times minus a plus, so it comes out as, in this particular case, 2 plus 2. So we've now got the partial fraction coefficients, and what we have to do next is to take the inverse Laplace transforms. So the first one is 2 over s. So we can get an expression now, y of t, and so we're going to get a 2, and then 1 over s is just 1, so that's 2 times 1 is 1, minus 4, then 1 over s plus 1 will be the same as e to the minus t. And then we've got a plus 2, and this time it's plus 2 here, so it's going to be e to the minus 2t. And then this then is the equation for the step response. As we put different values of t in here, we can plot a graph, and again we get a little graph which would look at something like this, and this would be a graph of y of t against t. This value along here, we call this the steady state value, and you can get this by putting t large into here. So that disappears, so that's going to be 2, isn't it? So this distance here will be 2 units. The exact shape we'd have to get by putting different values of t in, putting some points on, and and then joining the points out to get the graph. So that's another example now of going from a differential equation to a time domain solution, and those are just use these first two. Now the next one's a bit more complicated. We're going to use these two as well. So this one's a bit more, but you can see it's more complicated, but it's not that very complicated. Right, so now we've got another example we're going to do. This is again a differential equation here, and we're going to try and get the time domain to a step response to the system, and this time we're going to try and deploy these two down here which have got the sines and coses in. So this one's going to be a little bit more advanced than the previous one, but the first thing we do is convert this now into a transfer function, multiply the transfer function by the 1 over s, then convert it into partial fractions, then take the inverse Laplace transforms, and we get our time domain solution. So let's have a go at this. So d2y by dt squared will be s squared, so we get s squared times y plus 4sy plus 5y is su plus u. So we can then take out the y's and the u's, so we get s squared plus 4s plus 5 times y equals s plus 1 times u. Then take this term, so my pen's not working very well here. Take this term underneath here, so we get that y equals s plus 1 over s squared plus 4s plus 5 times u. And so now we have our transfer function for the system from our differential equation, and now we're going to multiply the transfer function by the step and then split it into partial fractions. So let's have a go at doing that. So we're going to have s plus 1 over s squared plus 4s plus 5 multiplied by the s, which is the step response. I'm just going to move this slightly. So you can have s plus 1 over s squared plus 4s plus 5. We just need a bit more space. We'll rewrite this now as a over s plus bs plus c over s squared plus 4s plus 5. So this time it's a little bit more complicated partial fraction, and the cover-up rule now doesn't work quite as well. So what we're going to do is we're going to multiply both sides by this term here on top. So if we multiply that on top, the first term will disappear and we get s plus 1. If we multiply this by this, the s will cancel, so we get a into s squared plus 4s plus 5. And then if we multiply this by this, we'll get bs plus c multiplied by, this will cancel with this, and we're left with the s. That's just multiplying everything through all this equation by this term here. Now we can do is we can do our compare coefficients to work out a, b and c. So let's have a look at this now. Which one should we go for first? Should we go for coefficients of, let's say, the term with no, so we've got 1 on this side, so it's coefficients of s to 0, so we've got a 1 on this side, and on this side we've got 5a, and we've got no coefficients of s. So we can get that a now is 1 over 5, so a is 0.2. So that's our first one done, a is 0.2. To the next one, we'll do the coefficient of s to the 1. So s to the 1 on this side, it's a 1 in there, so that's going to be 1. And s to the 1 this time will be 4a. And this time we'll have c. So now I've got the equation of 4a plus 1 plus c is equal to 1. But we know now that a is 0.2. So this is 0.8. So if 1 plus 0.8 adds up to 1, then c must also be 0.2. That's quite good. The last one now is to get the b. So to get the b, we need the coefficient of s squared. So on this side, there's no s squareds, and we've got an a here, plus ab. So we now know that a plus b is 0, but we know now that a is 0.2, and therefore b must be minus 0.2. It's going to be minus 0.2 there. So we've now got our transfer function split now into the partial fraction form here. So we can get away with this. Now this one's a bit more tricky. So we're looking now at this now, at our table here, to see how we're going to fit it. So we can see that the first term goes with this one, so that's quite nice. But now we've got a more complicated term here, and this one now doesn't seem to fit in with either of these, because this one doesn't factorise very easily. So we're going to try one of these now. So we need to write now s squared plus 4s plus 5 as s plus a squared plus b squared. As s plus a squared plus b squared. Work out what a and b are. So we can see from this now that if we make a as 2, then this is going to give us an s squared plus 4s plus 4. So this gives us s squared plus 4s plus 4, and therefore b squared must be 1. If b squared is 1. Right, so there we go now. So we've got our partial fraction form of this, and next thing we need to do is to convert this into a form of s plus a squared plus b, and we can do that by noticing if we put an s plus 2 in here, then we get s squared, 2 2's are 4, and another 2 2's are 4, 4 on that side, 5 on this side. That's got to be a 1. So we can rewrite now this term here as minus 0.2s plus 0.2 over s plus 2 squared plus 1. Now the problem we've got now is this term here now doesn't fit into either of these two formats here. So we'll have to slightly adjust it now to have this now will have to be equal to a combination of these two terms. So to do that, notice that we've got an s plus 2 here, and we have an s plus 2 in there as well. So if we start off with this term here, this could be split now into alpha into s plus 2 over s plus 2 squared plus 1, and then we have a beta over s plus 2 squared plus 1 as well. This term here would be that term, and this term here would be this term. And what we're going to do now is work out the alphas and betas. So if we multiply, this has got to equal to this. So if we multiply everything by this term, we can delete those. And so we can now see that alpha, so then we get essentially this equation, this part here. We've got alpha into s plus 2 plus beta equal to 0.2s plus 0.2. So looking at this now, the different coefficients, obviously alpha has got to be minus 0.2. That's going to be minus 0.2. And this is minus 0.2 and minus 2.2s, and this has got to be 0.2 at the end. Then beta, so this is going to be minus 0.4 plus beta is 0.2. So then the way we can achieve that is with beta as 0.6. So with beta as 0.6. Then we've got to include so that's this term here, is this one, which are these two. So if we include now the 0.2 over s, then we get our final Laplace transform formula. And then what we can do now is convert now this one back now into the time domain. So 0.2 over s, so we now get an expression for y of t equal to 0.2, because 1 over s is just 1. And I've got minus 0.2, that's this 0.2 here. Now I've got s plus 2 over s plus 2 squared plus 1, so that's one of these. That's going to be e. The a is 2 and the b is 1, so it's e to the minus 2t cos t. That's going to be e to minus 2t cos of t plus 0.6, got 0.6 in here, and this one now is one of these, so this is going to be an e to the minus 2t sine t. And this gives us our final expression now for the time domain response to the system. This y of t is 0.2 minus 0.2 e to the minus 2t cos t plus 0.6 e to the minus 2t sine t. And because we've got the presence of sine and cos terms, we're likely to get like an oscillatory response here. And so we could put different values of t into this, get some values of yt, get some points on here, like this, join them up, and we'd get the transient response. So there's another example now, slightly more complicated, of using these two terms in a differential equation to obtain a time domain response which has got some oscillatory behaviour with cos and sine terms in.